Sagittarius A is not what you think. Almost everything you were taught about the center of our galaxy is wrong. The one we've been calling a supermassive black hole for decades, it might not be a black hole at all. It might be dark matter. And as if that wasn't strange enough, this isn't just about the center. The same substance that could be sitting where the black hole should be might also be the thing holding the entire galaxy together, from the innermost light hours to the outermost halo. So, let's go there. Dark matter makes up about 85% of all the matter in the universe. We know it's there because of the way galaxies rotate. Stars on the outer edges of galaxies move far too fast to be held in orbit by the visible matter alone. Something invisible is adding extra gravitational pull. We call it dark matter because it doesn't seem to interact with light or regular matter in any way except gravitationally. It doesn't emit light. And yet, it makes up the vast majority of mass in the cosmos. Without it, galaxies would fly apart. We know that most galaxies are embedded in enormous halos of this stuff. What we don't know is exactly what happens at the very center. As Valentina Crespi, a researcher at the National University of La Plata in Argentina, put it, "We know dark matter has to be at the outskirts of galaxies, but we don't know what happens at the very center." And that's the question her team decided to answer. On February 5th, 2026, they proposed a model in which the central object in the Milky Way is not a black hole at all. Instead, it is a super dense core of a specific kind of dark matter, a kind made up of fermions. So what are fermions? Fermions are a class of subatomic particles. They include familiar things like electrons, protons, and neutrons. What makes fermions special is a rule they obey called the Pauli exclusion principle. Two identical fermions cannot occupy the same quantum state at the same time. This creates what's known as degeneracy pressure, a force that resists compression. It is the same force that holds up white dwarf stars and neutron stars, preventing them from collapsing under their own weight. The researchers propose that dark matter might be made of similar particles, neutral fermions that don't interact with light, but do interact gravitationally. And if those fermions have the right mass, somewhere in the range of about 50 to several hundred kilo-electron volts, then something remarkable happens. They don't collapse into a singularity. They can't. The Pauli exclusion principle prevents it. Instead, they form an incredibly dense but finite object. A dark matter core so massive and compact that it mimics the gravitational behavior of a black hole without actually being one. This is where the physics gets elegant. The model is known as the RAR model, named after the physicists Ruffini, Argüelles, and Rueda, who first developed it. It describes what happens when a large cloud of fermionic dark matter settles into gravitational equilibrium within the framework of general relativity. It considers the quantum nature of the particles, something that standard computer simulations of dark matter cannot do. And it self-consistently incorporates the Pauli exclusion principle, yielding a quantum pressure that dominates the behavior in the central region. In the outer regions of the galaxy, these fermions behave like a warm gas. They spread out, forming a vast, diffuse halo. This is the part of dark matter we already know about. It's the halo that explains why stars in the outer Milky Way orbit the way they do. But toward the center, something different happens. As more and more fermions are pulled inward by gravity, the density increases. And because fermions obey the Pauli exclusion principle, they cannot all collapse into the same point. Instead, they settle into a degenerate state, packed as tightly as quantum mechanics allows, but not infinitely so. The result is a dense core, fermion degeneracy pressure supporting it from within. The model predicts novel density profiles with a dense core and diluted halo morphology, one substance, spanning the entire galaxy. The dense core at the center and the diffuse halo at the edges are not two separate things. They are two manifestations of the same, continuous distribution of dark matter. As co-author Carlos Argüelles put it, They are not just replacing the black hole with a dark object. They are proposing that the supermassive central object and the galaxy's dark matter halo are two expressions of the same continuous substance. And the numbers work. For fermion masses in the range of about 50 to a few hundred kilo-electron-volts, the model produces a central core with roughly 4 million solar masses. Exactly what's needed to explain the orbits of the stars. At the same time, the outer halo matches the observed rotation curve of the Milky Way. The team used data from the European Space Agency's GAIA DR3 mission, which meticulously mapped how stars and gas orbit far from the galactic center. Their data revealed a slowdown in the galaxy's rotation curve at large distances, known as the Keplerian decline. The fermionic model explains this decline naturally, because it predicts a tighter, more compact halo than traditional cold dark matter models, which tend to spread out following an extended power law tail. This is the first time a dark matter model has successfully bridged these vastly different scales. From the stellar orbits measured in milliparsecs at the galactic center to the rotation curve measured at kiloparsec scales in the outer halo, there is one more detail worth mentioning. The model predicts that sufficiently degenerate fermion cores, those packed to their quantum limit, can reach a critical mass beyond which they would collapse into a supermassive black hole. This critical mass is determined by the fermion mass and general relativistic stability criteria. In other words, the same model that offers an alternative to black holes also provides a pathway for forming them. A fermionic dark matter core could exist stably for billions of years and then, under the right conditions, collapse to form a black hole. This introduces a new possible mechanism for supermassive black hole formation in the early universe, a problem that has long puzzled cosmologists. So here's the obvious question. If both a black hole and a dark matter core can explain the same star orbits, how do we know which one is actually there? The short answer is that right now, we can't. Not definitively. The researchers used a statistical method called Markov chain Monte Carlo, sampling to explore the parameter spaces of their models. They tested both the black hole model and two versions of the fermionic model, one using 56 kilo-electron-volt fermions with a lower core compactness, and another using 3 to 100 kilo-electron-volt fermions with a higher core compactness against the orbital data of the S2 star taken from observations collected between 2000 and 2019. What they found is striking. For every star and G source they tested, the difference in the predicted orbital parameters between the black hole model and the fermionic dark matter model was less than 1%. The orbits are nearly identical. The S2 star's semi-major axis, eccentricity, orbital period, and all 6 classical orbital elements came out almost exactly the same, regardless of which model generated the gravitational potential. That includes all the relativistic effects we've measured so far, the gravitational redshift detected in the light from S2 as it passed close to the center, the transverse Doppler effect of special relativity, the periapsis precession, the way S2's orbit slowly rotates with each revolution. Both effects are predicted by both models to within the current measurement uncertainty. Together with the tight S-cluster of young and bright stars around Sagittarius A, there exists a population of dust-enshrouded objects known as G sources, orbiting in the inner region of the galaxy. These objects have relatively long orbital periods. On observational grounds, they belong to a different family of sources than the stars. Their data is not yet precise enough to report relativistic effects. A somewhat controversial object among them is G2, which was first detected in the last decade and initially interpreted as a gas cloud in a highly eccentric orbit, expected to be tidally disrupted during its closest approach. However, the object survived, raising questions about its true nature. More recent analyses suggest it may be a compact stellar source surrounded by a gaseous, dusty envelope rather than a simple gas cloud. For the G sources, no conclusive preference emerged between models when computing Bayes factors. The data quality and orbital coverage of these objects is simply not yet sufficient to discriminate. In other words, the data fits both explanations. We don't yet have the precision to distinguish between them, but there are differences, and they are very specific. This is where it gets genuinely fascinating. Remember that famous image from the Event Horizon Telescope? The glowing ring with the dark center? Most people interpreted that as proof of a black hole, a shadow cast by an event horizon. But a 2024 study by Pauli and colleagues, also published in the monthly notices of the Royal Astronomical Society, showed something remarkable. When they simulated what a fermionic dark matter core would look like if it were surrounded by a standard accretion disk, the kind of hot, glowing material that spirals into massive objects, the images it produced looked almost exactly like the black hole images. The simulations showed a central brightness depression, a dark spot in the middle, surrounded by a ring-like feature. From a distance, it looked like a shadow. The central brightness depression arises from the drop in temperature toward the center of the dark matter core, due to the decay of viscous stresses in the disk, and secondarily, from the gravitational redshift of photons coming from that region. For Milky Way-like galaxies, the simulations found that the central brightness depression had diameters down to about 35 micro-arcseconds, as measured from a distance of approximately 8 kiloparsecs. These are angular sizes, consistent with what the Event Horizon Telescope actually measured for Sagittarius A. As Crespi explained, the dense dark matter core can mimic the shadow because it bends light so strongly, creating a central darkness surrounded by a bright ring. The model is consistent with the famous black hole shadow image. But here is the crucial difference. A black hole produces something called photon rings. These are created when photons get caught in the extreme curvature of spacetime near the event horizon. Their paths bend so sharply that they can orbit the black hole one or more times before either falling in or escaping. These additional loops of light create thin, nested rings in the image. Photon rings are a universal prediction of black holes under general relativity. The fermionic dark matter core does not produce photon rings. Because there is no event horizon, no point of infinite density where space-time breaks down. The core is dense, yes, extraordinarily so, but light that passes close to it bends by a finite amount and continues on its way. In the simulations, the maximum deflection angle for light in the dark matter core's spacetime is always less than 180 degrees, even for the most compact and degenerate configurations. That means photons cannot complete full orbits around the object. There are no secondary images, no photon rings. This is not a subtle difference, it is a structural one, and it could, in principle, be observed and tested. There is another important distinction worth noting. A defining feature of a black hole is its event horizon. However, early proponents of the Event Horizon Telescope argued that detecting a shadow would provide evidence for the existence of such a horizon. Since then, many researchers have studied what shadow features look like for different compact object alternatives, both within and beyond general relativity. Some have put constraints on black hole alternatives based on the non-observation of electromagnetic radiation from a putative hard surface. But as some theorists have argued, the observation of accretion flows only suggests the presence of some sort of one-way membrane of infalling matter. It cannot be interpreted as a definitive claim for an event horizon. And crucially, the fermionic dark matter core satisfies this condition. It has no emitting hard surface. Material that falls in simply sinks deeper into the distribution. There is no surface to glow. There is no horizon to mark a boundary. There is only an ever-increasing density of invisible matter. Sufficiently compact fermion cores, when close to their critical mass for gravitational collapse, can still reach the point where the light bending is dramatic enough to produce the observed shadow. But even at this extreme limit, the deflection angle never crosses the threshold needed for photon rings. It's a hard boundary set by the physics of fermion degeneracy. Now, there is another mystery at the galactic center that rarely gets talked about, but might be connected to all of this. It's called the missing pulsar problem. Pulsars are rapidly spinning, highly magnetized neutron stars that emit beams of radio waves sweeping across space like cosmic lighthouses. In the absence of any external influences, their pulses arrive with extraordinary regularity. They are essentially natural clocks of astonishing precision. Millisecond pulsars in particular exhibit extremely stable clock-like behavior due to their very rapid rotation. The galactic center, with its extreme density of stars, roughly 1 million per cubic parsec within the innermost parsec of Sagittarius A star, should be home to a large population of them. Models predict anywhere from 100 to 1,000 active pulsars in relatively close orbits around the central object. If we could find even one pulsar in a tight orbit around Sagittarius A star, we could use it to measure the mass, spin, and quadrupole moment of the central object with extraordinary precision. As researchers have noted, any external influence on a pulsar, such as the gravitational pull of a massive object, would introduce anomalies in the steady arrival of pulses, which can be measured and modeled. It would be one of the most powerful tests of general relativity ever performed. A pulsar in a very close orbit could even experience gravitational deflection of its pulses, enabling a probe of the strongly curved space-time geometry. But despite decades of searching, almost none have been found. The only pulsar detected near the galactic center is a magnetar called SGR J17452900, located less than 1/10 of a parsec from Sagittarius A star. The next closest known pulsars are more than 30 parsecs away. In early 2026, a team led by Karen Perez from Columbia University and the Breakthrough Listen initiative published results from one of the most sensitive pulsar surveys ever conducted toward the galactic center. They used the Green Bank telescope at X-band frequencies between 8 and 12 gigahertz, collecting more than 20 hours of data, with 11 hours focused on the innermost 1.4 arc-minutes of the galactic center. They identified a single intriguing candidate, an 8.19 millisecond pulsar signal, persistent in time and frequency across a 1-hour scan. If confirmed, it would be the first millisecond pulsar ever detected in the galactic center. But the team was unable to make a definitive claim due to mixed confidence from their statistical tests and because the signal was not detected in subsequent observations. Their survey reached luminosity limits sensitive enough to detect the most luminous pulsars expected in the galactic center, yet among over 5,000 signal candidates, only one showed promising characteristics. The scarcity of detections reinforces what researchers call the missing pulsar problem, the idea that strong scattering and extreme orbital dynamics may obscure pulsar signals in this region. The survey was also a computationally intensive effort. Individual observations lasted 1 to 2 hours, covered nearly 4 gigahertz of bandwidth, and each produced between 3 and 8 terabytes of data. But here is the thought worth considering. If the central object is not a black hole, but a distributed dark matter core, the space-time around it would be structured differently. The gravitational environment, while producing nearly identical stellar orbits, could influence the propagation of radio signals in ways we haven't yet accounted for. Our assumptions about the expected pulsar population are built upon the black hole model. If that assumption is incomplete, our predictions might need to be revisited. So how do we resolve this? There are several paths forward, and they are all converging on the same question. The first is better data on stellar orbits. The gravity instrument on the Very Large Telescope in Chile has already begun producing more precise measurements of the stars. The measurements from gravity have considerably reduced the error bars on S2's orbital data near pericenter passage compared to earlier datasets. The S2 star is expected to pass through its apocenter around 2026. New data from that passage will further constrain the models. One specific prediction is the rate of periapsis precession. The black hole model and the dark matter model predict different precession rates. For 56 kilo-electron-volt fermions, the model actually predicts retrograde precession, the orbit rotating in the opposite direction compared to what a black hole would produce. More compact cores, with fermion masses of 200 to 378 kilo-electron-volts, predict precession much closer to the black hole value. Once tested with a better resolution and larger dataset, including the 2026 apocenter passage, the results should help constrain these competing predictions. The second path is imaging. The next-generation Event Horizon Telescope is being developed, with potential space-based instruments that would extend the interferometric baseline far beyond what's achievable from Earth alone. Future arrays integrating space-based instruments are expected to enable measurements of the photon ring structure. If those instruments confirm the presence of photon rings, the black hole model holds. If they confirm their absence, the dark matter core model gains significant support. The third path involves the GAIA mission. The fermionic model predicts a specific shape for the galaxy's rotation curve at large distances. The most recent GAIA DR3 data already shows hints of the Keplerian decline that the model predicts. Future data releases may strengthen or weaken this signal. And if a pulsar is ever confirmed in a close orbit around Sagittarius A star, perhaps the candidate detected by the Breakthrough Listen team or another yet to be found, that could be the most powerful test of all. A pulsar's clock-like precision would allow us to map the space-time geometry in extraordinary detail. It would tell us whether we're dealing with a singularity hidden behind an event horizon or a dense but finite distribution of matter. Here is what we know for certain. Something massive sits at the center of our galaxy. It has roughly 4 million times the mass of our Sunday. It bends light. It drags stars into furious orbits, and it casts a shadow that our telescopes can photograph. What we don't know, and what we are only now beginning to seriously ask, is whether that thing is what we've always assumed it was. The black hole model is powerful. It has decades of theoretical support and a wealth of observational evidence, but it has always been an inference. We have never directly observed an event horizon. We have never measured a singularity. What we have measured are orbits, redshifts, precessions, and images. And, as it turns out, a dense core of fermionic dark matter can reproduce all of those measurements to within the precision of our current instruments. The fermionic model does something the black hole model cannot. It connects the center of the galaxy to its edges. It provides a single, continuous explanation for both the violent motion of stars at the core and the gentle rotation of material tens of thousands of parsecs away. One structure, from the innermost light hours to the outermost halo. That elegance carries weight in physics. When a single model can explain what previously required two separate assumptions, the combination of a central black hole plus a separate dark matter halo, it demands serious consideration. The researchers found that while current data for the inner stars cannot yet decisively distinguish between the two scenarios, the dark matter model provides a unified framework that explains the galactic center and the galaxy at large. That unification is rare in astrophysics, and it demands attention. There is something humbling about this moment. We spent decades building an increasingly detailed picture of a black hole at the heart of our galaxy. We named it, we measured it, we photographed it. And now we are being asked to consider the possibility that we were photographing something else entirely. Not a hole in space-time, but a mountain of invisible matter so dense that even light is forced to bend around it. We don't yet know which model is correct. The data does not yet allow us to choose, but the tools to answer this question are coming. Better telescopes, more precise instruments. Perhaps, eventually, a pulsar ticking away in the darkness, close enough to the center to tell us what's really there. For now, all we can do is look toward the center of the Milky Way and wonder, is it a black hole? Or is it something stranger, something older, something woven into the very fabric of the galaxy itself? The more we study it, the less certain we become. And that, perhaps, is the most exciting thing of all. Because in science, the moment you stop being certain is the moment you start making real discoveries.